Hey everyone, welcome back to the channel. Today we are going to start a new playlist called Data Structures and Algorithm, and we'll be diving into essential DSA problems, one of which we'll be tackling today, which is from LeetCode, and the name of the problem is contains duplicate. If you're preparing for coding interviews, this problem is a must know. Why? Because it tests your understanding of basic data structures like arrays and sets, which are building blocks for many other problems. Plus, solving this kind of problem efficiently is exactly what interviewers are looking for. So stick around because we will not only solve it, but also learn the techniques so you can apply to similar problems. So for the agenda, here's what we are going to cover today. First, we'll understand the problem statement and go through a few examples to clarify what's expected. Next, we'll plan out two solutions, a simple brute force approach and an optimized solution using hashing. Then we'll implement both solutions step by step in Python. Finally, we'll test our code with multiple examples and analyze the time and space complexities to understand why the optimized solution is better. By the end of this video, you'll be ready to solve this problem with confidence and use the same approach for similar questions in interviews. Alright, let's get started by understanding the problem statement. The title is Contains Duplicate, and it's a common problem under arrays and hashing. Here's the challenge. The question says, given an integer array nums, return true if any value appears at least twice in the array. Return false if every element is distinct. So the problem says that it gives an input, is a given input, and which is an array of integers called nums. The output should return true if any value appears at least twice in the array. Otherwise, return false. In simple terms, we are checking if there's any repeated number in the array. If we find at least one duplicate, we return true. If there are no duplicates, we return false. Let me show you some examples to make this clear. Let's take this example. The array of nums is 1, 2, 3, and 1. Let's write it here. Nums 1, 2, 3, and 1. So what we'll do is we'll start with the first number. We'll check if we have seen this before. As this is the first number, we haven't seen this, okay? Now we'll move on to the second number, which is 2. So we'll ask that if we have seen this number before. So we haven't seen number 2. So what we'll do is we haven't seen this number. Okay, now let's move on to the third number, which is 3. Have we seen this number? No, we haven't seen this number. Let's move on to the fourth number. The fourth number is 1. So have we seen this number before? And yes, we have seen this number before in the first place. So the output would be true. In this example, the number 1 appears twice, once here and then here. Since we found a duplicate, the output is true. Now let's take another example. Let's call it example 2. And here we have nums, which is 1, 2, 3, and 4. What we'll do is here, we'll start with the first number in the index of 0. The number is 1. Have we seen 1 before? No, we haven't. We'll move on to the second number. Have we seen 2 before? We haven't seen that. We'll move on to the third index, which is the second index. And have we seen 3 before? We haven't. We'll move on to the fourth. fourth index, which is the third index. And have we seen 4 before? No, we haven't. So our output would be false. Here in this example, every number is unique, so the output is false. Now let's address some common clarifications you might have when solving this problem in an interview. One question can be that the array can be empty. There's an empty array which says, let's say, nums, and according to constraints, that cannot happen because the input array will always have at least one element. The second clarification is, what should I do if all the numbers in the array are duplicate? For example, we have nums where all the elements in the array are duplicate. So if that's the case, if all the numbers are duplicates, we only need one duplicate to return true. So for example, if that's the case, we'll output true. Third clarification is, how large can the number be? How large can the array be? So we can say that in the constraints we are given that the array can be as large as 10 to the power of 5, which is 100,000 elements in an array. That's why we need to think about efficiency when solving this problem. Now that we understand the problem and its requirements, let's move on to planning our solutions, starting with a simple brute force approach. So the idea here is simple. For each number in the array, let's take an array. We'll take the array 1, 2, 3 and 1. The idea here is simple. For each number in the array, we compare with every other number. If we find a match, we return true. Here's how it works step by step. Let's say our input is nums equals to 1, 2, 3 and 1. We'll take the first number 1 and we'll compare with every number after it. Then we'll move on to the second number, which is 2. We'll compare this with every number after it, which is 3 and 1, and so on. Now what we'll do is to take this and write a pseudocode for this. Here's the pseudocode for this approach. Our first step will be, for each element in the array, which is nums of I, we'll compare it with every other element. And how would that be? It would be something like nums of I is equal nums of j. And if nums of I is equal nums of j, will return true. No duplicates are found. No duplicates are found. Then we'll return false. So this is the pseudocode for our brute force approach. Now, while this solution works, it has a major problem. It's slow. Let's talk about the time complexity. So what we are talking about here is that we will have two loops, the outer loop and the inner loop. The outer loop will run in the n times, and the inner loop will be running n minus 1 times. This means the time complexity of this approach is n squared, which makes this solution impractical for large arrays. Let's take the constraint. For example, if we have the array with 100,000 elements, this approach would take around billions of comparisons. Now, to solve this problem efficiently, we can use a data structure called a set. A set is like a list, but it doesn't allow duplicates and it's very fast at checking if an element already exists. Here's the idea. As we iterate through the array, we'll keep track of the numbers we have seen so far in a set. If we encounter a number that's already in the set, we return true. Otherwise, we add the number to the set and move on. Let's walk through the same examples with this optimized approach. Let's say we have an array of nums, which is 1, 2, 3, and 1. Let's take the same example. What we'll do is we'll initialize a set called scene with our curly braces here. Now we look at it step by step. Look at the first number, which is 1. Is 1 in the set? No. Then add this 1 to the set. Let's look at the second number, 2. Is 2 in the set? No. What we'll do is we'll add it to the set. First we have 1. Now we have 1 and 2 in the set. Look at the third number. There's 3. Do we have this in the set? No, we don't. So we'll add this. Now it's 1, 2, and 3. Look at the fourth number. The fourth number is 1. Do we have 1 in the set? Yes, we do. Now we have found the duplicate. We'll return true. Now let's talk about the pseudocode for this example. For the pseudocode of this example, we'll start with creating an empty set. Create an empty set. We'll name it as scene. The second is for each element. For each element in the array, if the element exists in the set, what we'll do, we'll return true. Otherwise, we will add that element to the set. Add the element to the set. We'll add the element to the set if it's not in the set of scene. Lastly, After iterating through the array and we didn't found any duplicates, we didn't find any duplicates, we'll just return false. Now we have a pseudocode for the optimized. With this approach, we only need to loop through the array once, checking if an element is in the set and adding elements to the set are both O of 1 operations. The total time complexity is O of n. The total time complexity for this approach is O of n, which is much faster than the brute force approach. The space complexity for this approach is also O of n, because we are using extra space to store the set. Now we have two approaches, the brute force solution, which is simple but inefficient, and the optimized solution using hashing, which is both faster and practical for large datasets. Let's implement these solutions in Python and test them out. Let's start by coding the brute force approach. As a reminder, this solution compares each element with every other element in the array. Here's how we write it in Python. We'll say def, which is the function, contains duplicate, which takes in nums. For I in range length of nums, for j in range I plus 1, and length of nums if nums I is equal nums of j, then we'll return true. And if we couldn't found any duplicates, we'll return false. Here we define a function named containsduplicate, which takes a list of integers nums as input. In Python, functions are defined using the def keyword. The outer loop for I in range length of nums loop iterates over each index in the array. The length of nums function gives us the total number of elements. Variable I keeps track of the current element as we are comparing. For the inner loop, for j in range I plus 1, length is nums. This loop compares the current element, nums of I, with all subsequent elements, which is nums of j. Notice the I plus 1. This ensures that we don't compare an element with itself or any elements before it. Let's take an example here. Nums. It will make our clarification easier. So here we are saying that what we are doing is the I plus 1. This ensures that we don't compare an element with itself or any elements before it. The comparison if nums I equal nums j. This line checks if two elements are equal. If a match is found, we immediately return true. If the loop finishes without finding any duplicates, the function returns false. While this solution works, its time complexity is O of n square, making it very slow for large arrays. That's why we need a better approach. Now let's move on to the optimized solution using Python's set data structure. Sets are incredibly efficient for checking membership, which makes this approach much faster. Now we'll write the code for it. Def contains duplicate, which takes in the nums array. We'll initialize an empty set, scene set for num in nums. If num in scene, what we'll do, we'll just return true. Also, we'll add the number to the set. How we can do that? Scene.add, add and takes a num. And if no duplicates are found, we'll just return false. That's it. That's our solution for the optimized one. Now let me explain this line by line. We create an empty set named scene using set. A set in Python stores unique elements and provides fast membership checks in O of 1 time. For num in num, this loop goes through each number in the array one by one. If num is in scene, checks if the current number already exists in the set. If it does, we immediately return true because we have found a duplicate. If the number isn't in the set, we add it using scene.add num. If we finish the loop without finding any duplicates, we return false. This approach is much faster with the time complexity of O of n and a space complexity of O(n) for storing the set. It's a great example of how using the right data structure can drastically improve performance. Now you have seen the brute force and optimized solutions. In the next section, we'll analyze the performance of these solutions and compare their time and space complexities in detail. Now we're going to manually test our containsduplicate function with different inputs. By doing this, we ensure our solution works correctly and understand how algorithm behaves with various cases. We'll test both brute force and optimized solutions using Python. For simplicity, we'll focus on the optimized version using a set, as it's the most efficient. Our first test case is nums 1, 2, 3, 1. Let me write it down. 1, 2, 3, and 1. We expect the output to be true because 1 appears more than once. Let's walk through the algorithm step by step and visualize how the set evolves. Our initial input nums 1, 2, 3, 1. For the first is 1 is seen. No, then we add 1 to scene. And now scene becomes 1. We'll go to the second one. Is 2 in scene? No. Then add 2. Now the scene is 1 and 2. We go to the third one. Is 3 in scene? It isn't. So we'll add 3 to it. Now scene is 1, 2, 3. Now for the fourth one, is 1 in scene? Yes, duplicate is being found and will return true. So as soon as we encounter 1 for the second time, the algorithm identifies it as duplicate and returns true. This matches our expectation. Now let's take another example. Let's do 1, 2, 3, 4. Here what we have is, we'll go again one by one. Is 1 is in the scene? No, we don't. We'll add 1 to the scene set. Is 2 in scene? No, we'll add it to 1 and 2. If 3 is in scene? No, it isn't. We'll add 1, 2, 3, 4. Is 4 in scene? No, it isn't. We'll also add this to 1, 2, 3, 4. And there's no duplicate, so we'll return false. Here every number is added to the set without encountering a duplicate, so the function correctly returns false. Let's take one other example, which is all the numbers are 1, 1, 1 and 1. So we'll start with the first one. Is 1 is in scene? No. Let's add 1 to the scene. If 1 is the second number, which is a 1 also, is in the scene? Yes, the duplicate has been found and will return true. As soon as the second one is encountered, the function identifies it as a duplicate and it stops processing further, returning true as expected. Finally, we'll test the smallest possible array with just a single element, which is 1. Since there's only one element, there can't be any duplicate, so the output should be false. Let's start. We initialize the inputs, num is 1, and we initialize our set, which is scene, to be empty. Is 1 in scene? No. Then we'll add 1 to the scene. And that's the end of the array. So no duplicates are found, and then we'll be returning false. With only one number in the array, the algorithm correctly returns false. There are no duplicates. By manually working through these test cases, we've confirmed that our function works correctly for different scenarios. Arrays with duplicates, arrays without duplicates, and edge cases like a single element array. If you're debugging your solution, always test with a variety of inputs to ensure it handles all edge cases. Now that we have seen both the brute force and optimized approaches in action, let's analyze their performance. We'll start with the brute force approach and break down its time and space complexity. The first loop runs n times, where n is the length of the array. For each element in the first loop, the second loop runs up to n-1 times. So in the worst case, the number of comparisons is roughly n into n-1 divided by 2, which simplifies to n square. As you can see, the time complexity grows very quickly as the array size increases. For large arrays, this becomes impractical. For example, if the array size is of 100,000, the number of comparisons would be in the order of 10 billion, which is very slow. In terms of space, the brute force approach doesn't require any additional data structure. It only uses a couple of variables for the loops. Therefore, the space complexity is O of 1, which is constant space. Now let's talk about the optimized approach using the set. This solution performs much better than the brute force approach. Let's analyze its time and space complexity. In the optimized approach, we use a set to store the elements we have seen so far. The key here is that checking if an element is in the set and adding an element to the set both takes constant time, which is O of n. Let's break it down. We loop through the array once, single iteration. For each element, we check the element is in the set, which takes O of 1 time. If not, we add it to the set, which also takes O of 1 time. Thus, the overall time complexity is O of n, where n is the length of the array. This is much more efficient than the O of n square in the brute force approach. In terms of space, the optimized approach uses a set to store all the unique elements from the array. In the worst case, when there are no duplicates, the set will store all n elements. Therefore, the space complexity is O of n, since we may need to store up to n elements in the set. So the question arises, why the optimized solution is more efficient? And the answer is that by using a set, we can reduce the number of redundant comparisons. In the brute force approach, we compare every pair of elements, but in the optimized solution, we only check each element once against the set. This eliminates the need for multiple comparisons and allow the algorithm to run in linear time, even for large arrays. As a result, the optimized approach scales much better with large datasets, making it much more suitable for real-world applications. So to summarize, the brute force approach has a time complexity of O of n square, and a space complexity of O of 1. For optimized approach, using a set has a time complexity of O of n, linear time, and a space complexity of O n, also linear time. For larger datasets, the optimized approach is clearly a better choice, as it dramatically improves performance. And that brings us to the end of today's lesson on contains duplicate problem. Let's quickly recap the key points we have covered in this video. First, we discussed the problem statement and how the goal is to identify whether any number appears more than once in the array. We began by exploring the brute force solution, where we compare each element with every other element. This approach works, but it's inefficient for larger arrays due to its time complexity of O of n square. Then we optimize the solution using a set. By leveraging the properties of a set, we reduce the time complexity to O of n, making our solution much more efficient, especially for large datasets. Lastly, we analyze the time and space complexity of both solutions. Understanding complexity is crucial in technical interviews because it helps us evaluate the efficiency of our solution. That's all for today. If you found this video helpful, make sure to like and subscribe so you don't miss the next one. Keep practicing, and I'll see you in the next lesson.